Okay, so welcome back. Just a few remarks where we are. So we talked about motivation for looking at power markets by taking away the assumption of being price taker and considering price maker. And the fact that this game gives rise to game because each player's cost function and profit and utility is coupled with what other players are also doing. And we looked at games with continuous action, and we looked at Cournot and Bertrand model. We looked at how we characterize their equilibria, whether under which conditions Nash equilibrium exists, and one way to compute it by connecting Nash equilibrium problems with variational inequality problems. So in the note, there are a lot of additional references both to my work with my colleagues and also just general reading on this topic. So, and everything I say here is in the note. So don't worry about kind of trying to copy everything. Everything is there with more examples and more exercises. So feel free to read that. But now we're going to talk about auctions. And so one good thing about teaching like a game theory session is that you can also play games. So we're going to play a game. And so basically, we're going to, the plan is I briefly tell you about two auctions. So how many people have heard of first price and second price auctions? Okay, a few. Good. I'll briefly tell you the auction rules are really simple. And then after that, we're going to look at sort of the properties of these auctions from the game-theoretic perspective, and then we're going to go into this a more sophisticated auction mechanism, which is a generalization of second price auction. It's called a VCG mechanism. But let's just start simple. And let's say that, so I want you to form groups of maybe 3 or 4. And one of you will be like, one of you wants to, is the system operator who wants to procure, let's say, 1 megawatt of capacity, and then the 2 or 3 of you are generators, and you have to decide what you offer for how much price, okay? And you don't talk with each other, you just have to choose the price, and maybe randomly you pick one to be renewable, one to be coal-based, and other types of generators. You can choose your type. And then without talking to the other person, you write your bid and give it to the system operator. And in the first price, in both first price and second price mechanism, the winner with the, since now this is a reverse auction, we want to buy from people, we pick the winner with the lowest cost, okay, lowest bid, okay. In the first price, though, the payment we make to the winner is exactly their bid. It's also called a pay as bid. So if, for example, I bid 5 euros for this 1 megawatt and my bid wins, then I get 5 euros. In the second price auction, the winner is still the one with the lowest bid, but the price that she'll get is the second lowest bid, okay? So if I bid, yeah, exactly. So if I bid 5 and the second lowest bid is 7, then I get paid 7. Okay. So let's say maybe we say this half of the class plays first price auction and this half second price auction, and you just form a group of 3 or 4 and pick who's going to be the system operator and what type of generator you are, and write your bids. And let's just do this for 3-4 minutes just to get started into thinking about how should players kind of strategize. Good. Shall we discuss? Okay. Let's see. Good. So let's. So did you guys come up with a winner and the payment? Let's hear maybe from first one from this side and one from this side. So is there a group who wants to share their result? This side. You guys were a group? The two and with the four. Okay, good. So do you want to share what happened in the your first prize? You're the operator. Okay.
And I had bits of 30 and 2 and 666.
Wow. Yes.
So the winner was 666.
Ah, okay. So you're doing a forward auction. The winner would be 2, I guess, because you're getting the one with the lowest bid. But yeah, if you are doing a forward auction, if you had an item for sale, yeah, of course you would give it. Yes, good. And so, so from the perspective of the bidders, how did you come up with your bids?
Structure is simple. I guess structure is like this: the lowest bidder will be the first dispatched one to the system. In power markets concept, I thought.
I'm just asking about your problem. I'm just asking about how you came up with your bids. Would you like to share? Yes.
It was just a coincidence.
It was just a coincidence. You randomly picked. What did you pick?
30.
30. Okay, good. Yeah, so just randomly.
Yeah.
Good. Yeah. Huh?
It's not a good strategy.
So the one that bid 2, how
Who-
would you recover your cost?
Yeah. Who bid 2? Did you bid 2? What did you think of did you think you're a renewable or?
I thought renewable. I mean, the marginal cost is so low. I mean, even might lead to the system negative prices, like in Germany.
Mm-hmm.
All the time.
Yeah, I know it's a little fuzzy, it's a little hypothetical, but lowest bidder.
Okay. Mm-hmm. And then 666. How did you come up with?
I think it wasn't so clear that how practical the example we were trying to make.
Okay.
We weren't trying to constrain it. We just said,
Okay, you just sort of randomly. Yeah, fine. Good. And then from this side, thank you for
In our
sharing.
case, we played one round basically of 30 market because we had only 2 bidders. So I bid like 1 million euros per megawatt hour, and it was second best bid. So
What
she got
did you
like 1
bid?
million euros per megawatt hour.
1 million.
It's like playing 30 on the market. If there is not enough suppliers, then we could
Okay.
split the profits later on. for
So you
example.
knew that there are not many other
Yes,
participants.
and then I can push up the price, and
Yes.
we can somehow later on basically get me also the money.
So you also bid high.
No, she
No,
went
I
with
bet
8.
like it was I bid 8 and he bid 1 million.
But then you don't win, right? So you won.
Yes, but if it's a
Yeah, you did a
but
collusion. Perfect. Good. So we'll discuss. Very, very good. And yeah.
But in long term and in honest market, it makes sense to bid close to marginal cost, because otherwise you have the danger of getting too low price and taking losses.
Good, yeah. But I guess if you kind of have information and you can continue to gather information about the market, then you can try to learn what could be the best. And if you know there are people whose cost is lower and they underbid you, yes, yeah. But you can, of course, have this collusion situation, yeah.
I'm sorry. Can I? Thank you. Argue against you actually, because if everyone does the same reasoning as you, everyone bids close to their marginal cost, and I bid 0, which is what I did in my auction. I won the auction, but I get the second lowest price, so I actually get my marginal cost down, and I'm basically sure that I'm going to win the auction. So, yeah.
what happens if you have more than bid, more?
But if you bid,
That's the problem. You have to be confident that you are smarter than the rest.
so you bid lower.
Yeah, so I bid at 0, and then we had a 20, a 250, and a 50, and I bid 0 under the assumption that they would bid something higher, something higher than that, which would allow me to recover my cost, because I knew I was gonna win and get the second lowest.
Okay.
Does that make sense? This is an example, right? So,
Yes, it's a risky strategy.
yeah.
Assume that you can recover because you know what the others would bid, right?
I don't know it, but I assume that. Yeah, exactly. Next round, we would all bid at 0, and we start going negative.
What's interesting, it shouldn't work, let me see, there seems to be a problem. Well, let's come back to that. Okay, but I just want to anybody else wants to share something? Okay, so what you notice is maybe, if I try to summarize, it's sort of hard to know what you should bid because you don't know what the other participants may be bidding, and of course you want to make profit, but how much profit can you make, and also the problem of collusion but the goal is to try to look at these problems using game theory, and hopefully we get some idea of, in the equilibrium, what's a bidding strategy that's equilibrium, which means that no player has incentive to deviate, and what would that mean in terms of the auction revenue and players' utility. Okay, so if we just it's exactly the structure of like a game that we introduced. So there are n participants, and here we have this additional notion of type. It means that what is each player's kind of, maybe in this case, the marginal cost or the amount it takes you to produce the electricity. And then the strategies are, again, the bids you offer. And then the difference is that there is a central operator or an auctioneer that gives you then the payment rule, okay? So then your utility is so it's the payment you get in the reverse auction minus your true cost. Okay, so in the first price auction, then if you're the so the winner is mean of j from 1 to n, and so this is called the choice, the social choice function, and then the payment Pj is equal to exactly, so let's call this J star, argmin, and the P to J star is exactly xj star, okay, for the winner, and so this is the winner, and it's 0 otherwise, okay. And then you can see that, I mean, this is just putting math into it. It's more intuitive if you just think about it as a winner. Then if you bid your true cost, you're going to make 0 profit. So you don't have incentive. If you want to make profit, you have to overbid, right? Okay, so as a participant, this is called also a pay-as-bid market. Because you're getting paid what you bid, if you bid your true cost, then you make no profit. So it's better to bid something that you make a profit. In the second price, the choice function is the same. So J star is exactly argmin of xj 1 to n, but Pj star for the winner is mean, take away the J star, so J not equal to J star of xj. So it's the second lowest bid. So in this case, actually the payment you make doesn't depend on the bid you made. Yes?
I just have a reflection on this.
Yes.
Because it seems like we assume that this is the only place where we can sell our goods as a bidder. It seems like this auction is the only place where we as a bidder can sell our good, right? Because otherwise we may consider the opportunity cost or so.
Yeah,
or
that's
what
a
we
good
could
point. I think that's part of it is reflected into what is the true value of this 1 megawatt, for example, to you. That depends on the opportunity, because then it's quite, also it's hard to know, because if you can sell your capacity in another market, or if you can participate in other markets, you may have an estimate of what's your true value, but you may not know it exactly. That's a good point.
Yeah, and it may not be the marginal cost, right?
Yeah, that's right.
Yeah.
This is just what is the true value. Let's not call it marginal cost, but it's what's the true value to you. Yeah. So it turns out that in the pay-as-bid, as we saw, to make profit, you have to you have to overbid in case of reverse. So I wrote the notes for my course because it wasn't mainly the course on game theory wasn't focused on electricity market, so I was looking at a forward auction, and we had a painting auction in the course when I brought posters to the class, and people bid for having this. So it was a forward auction, so everything was mags, and now I have to kind of reverse it in my mind. So sorry if sometimes in the note also there is in the terms of mean, and sometimes it's max. So whereas here, so we can show that in the second price auction, the Nash equilibrium. So Nash equilibrium is defined as before. So each player has no incentive to deviate from the offer. And in the second price auction, we can show that the optimal strategy is to bid truthfully. So the Nash equilibrium strategy, in second price auction is bidding truthfully. So meaning that if you know your true value is this T, you should submit that. You have no incentive to deviate from that, okay? And there is a proof, maybe we briefly go through it. But this property is called incentive compatibility. I think maybe Jalal mentioned it also yesterday. It's a property we hope to have for an auction, okay? And in the first example, in the beginning of the lecture where I showed you the LMP, the market, you saw that it's not an incentive compatible. This LMP pricing is not incentive compatible because you can increase your profit by overbidding, okay? So let's talk about this, why that's the case. The intuitive idea is that the amount you get paid doesn't depend on what you bid, okay? So the way to analyze it, and I have written the proof here in the notes, so you can go through it, but it's sort of a well-known property of second price auctions. Basically, you can analyze. This is, I'm looking at the case of a forward auction, so auctioneer wants to sell an item, so it picks the maximum bid. That's why you see the maximum over there. But you can sort of think about two cases. So if you overbid and if you underbid. Now let's go through the overbid case. This is so if you overbid xj, you give a xj that's greater than your true value. Then you can think of three cases, whether the second highest value is less than if it's less than your true value, then overbidding and truthful bidding both result in winning the auction with the same profit, so you don't have incentive to deviate. If the second highest bid is greater than your bid, then in either case you will lose, so you don't have your profit is zero, so you don't have incentive to deviate. If you're overbidding and you're overbidding greater than the second highest value, and that is also greater than your true value, it means you will win, but you make a loss because the amount you get paid, you have to pay for the item in the forward auction is greater than your true value, okay? So you have no incentive to deviate from truthful bidding, at least in theory, under this sort of sterilized model of the auction. And you can similarly go through the case of underbidding. So the second price auction is known as incentive compatible mechanism. And then the question is, okay, it seems it's a good idea to use this in electricity markets, and how can we generalize this? So let's do one more example. When you, let me just put one more example on the board. Actually, maybe it's here, then I don't have to. So it's incentive compatible. Okay. And this is the example that you can briefly pause, think about how would you suppose that we want, it's a slightly general model. So again, there is an operator that wants to purchase, let's say, 800 kilowatts of capacity, and there are three providers, and I will write them here so we can refer to them later. Player 1, player 2, player 3. So let me just copy it so you have a table. And these are the bids. 400 kilowatt, 25, I used Swiss francs, hope you don't mind. 600 kilowatts, 30 CHF, and then 200 and 400 kilowatt, 24 CHF, and this one places 400 kilowatt for 26 CHF and 200 kilowatt for 18 CHF. Okay. Okay. So it's what this means is that players can place multiple bids, but they're conditional bids, meaning that only we can accept one bid from each player. Okay. And so how would you define the second price? You wanna purchase 800 as a system operator. How would you define second price in this case? Who is the winner? Maybe the second question is easier to answer. Who is the winner, and what payment we should give them? Who is or are the winners? What payments to make? And let's maybe while I erase the board, you can just think about it. At least about who's the winner, you can think about. And then we're going to go to generalized second price auction. Actually, okay. See, so let's briefly talk about the winners. What's the cheapest way we can get 800 kilowatts? Let me hear from somebody I haven't heard before. And you have the microphone. Yeah. Can you pick somebody and throw it to them? Oh.
So you can pick the 200 from player 3 and the 600 from player 2. I think that's the cheapest option.
Okay. I think that's correct. That's the lowest. Good. And what payments we would make to them?
So it's second price. So we would pay them. What's the price of the 30 or?
The price of? Why? Like, so first of all, there are two people we have to give a payment to.
Yeah.
And how much we should give to each? Yeah, it's a bit maybe harder to see it, and exactly, good, thank you. Does anybody have something to add? Okay, if not, we're just gonna basically make, the reason it's not straightforward like the example we did is because we have multiple bits, and we have to figure out a way to generalize this second price. So what is the second price, okay? And that's where the concept of the VCG mechanism comes, and it's named after three economists, Vickery, Clark, Groves, who subsequently generalized the second price auction. One of them got the Nobel Prize, I guess. I don't now remember which one. It might be Vickery, I think. And so basically the idea is that we want to have a mechanism that's incentive compatible, and it turns out all the mechanisms that are incentive compatible are some variants of this VCG mechanism. And the idea is exactly like second price. We give a payment that by taking away that bidder, the winner from the game and resolving the problem, and give the payment to them that sort of takes away their contribution so they don't have incentive to game the market. Yeah? Are there two that gave 48? I don't. 48, I think, is the lowest. I think with the 600 from player 2 and 200 from player 3, you can get, this is 18. Sorry about that. Yeah. Okay. So we just maybe like introduce again, we just need some notation. So nothing complicated, but let's say that each player now can offer a bid vector, and let's say this is the cost or the price offer or price, and then this is the amount. And each of them could be multiple CJ1, maybe CJ and J. There could be a multiple set of pairs of price and amount. Okay. This, by the way, this example, I mean, this sort of multiple bids, at least in Switzerland, the ancillary service market is run exactly like this. Each participant gives a block of possible amounts and prices, and they're called conditional, meaning only one of them should be accepted from each player. And you can also generalize this setting to curves, bid curves. So instead of just saying, instead of just giving points along the M and C, you can just give the curve by, for example, giving the coefficients. And in the papers that we looked at, I cited, we looked at the more general model, but I start here because it's easier to explain. Okay. So then we also, now a mechanism is defined by two things. One is called the choice function, so which tells who is going to win, and the payment rule. Okay, and for the choice function, we're going to use the variable delta. So delta J is 0, 1, and J, if I stack them all together, then I get delta 1, delta N. It just says which bid is. If delta Ji is 1, it means the bid of player J, the ith bid of player J is accepted. Okay, choice function and then a payment rule. So there is a payment that goes to each player, Pj, payment to player J. And then, because it's a power market, then we have some constraints. How much we want to procure. Or, for example, in ancillary service market in Switzerland, you have some stochastic constraints on the bid. Whatever it is, we just say that constraints, we put them all together, and we say that the delta and M should be inside some constraint set. Okay? So C, it's a constraint set. For example, in the one we saw, it means that the sum of, you can easily encode that sum of the bids should be greater than or equal to, or should be equal to 800, right? This is just a 0, 1 vector, and this is you can multiply it by the bids and encode that you need 800. Okay.
You said the stochastic constraint set.
Yeah.
I didn't understand.
I'm just saying that this C could be of any type. The point is that you get some, for example, any complicated constraints on the amounts, I can encode it by saying delta M belong to some set. This set could be complex. Yeah, that's exactly how we modeled it. But basically, it just tells you how much you need to procure, and that the function may be any type. And then there is the cost for the auctioneer. And I'm looking at, by the way, one-sided markets. You can generalize this to two-sided, but it's easier to start like this. It's going to be C transpose, which is the vector of prices times delta. Is that clear? So, and let's write that as J of X. So let's just see what's happening. The players are giving the prices and the amounts a vector. Each player is giving a vector. The auctioneer has a choice function which decides which bids are accepted, and the way it does this normally is by minimizing this function subject to some constraint. So so let's say this choice function in pay as bid and VCG both is determined as, so delta star is argmin of J of X, which is equal to C transpose delta subject to delta M in C. Okay, makes sense. Like we will pick the bids that minimize procurement cost, whether you're pay as bid or VCG. But where pay as bid and VCG differ is that in the VCG, now we have to define what's the second price. And the way we do it is we look at the problem of removing the winner. So let's define J of X negative J as, actually call it J star, the minimum of J of X negative J, well, it's easier to say it in words. C transpose, C negative J transpose delta negative J, I'll explain in a second, subject to delta negative J, M negative J in C. Okay, what it's saying is that you remove player J's bid and you compute the optimal cost, okay, if this player was not in the market, and then what we will give them is, just to make sure I get the notations, Pj of X in the VCG is equal to J star of X minus J minus J star of X minus Cj transpose delta star of J. A lot of bookkeeping for all J winners. Oh, I just realized in the notes I wrote this for when you're doing a forward action, so you're picking the maximum. So let's see if any negative I need to put somewhere. Let me think. Minimum. Or just, if you don't mind, I will change this to max because I want to make sure I'm consistent with the notes. Then when you read your notes also, there's no problem. Okay, so let's say we are doing a forward action. So auctioneer will accept the bid that provide the highest value. Okay, is that clear? I hope I didn't cause confusion. Okay. Then the payment is you take away player J from the market, you compute the optimal cost, okay? And then what is the second term? So this first term, is cost, the optimal cost when player J is not in the market. The second term is the optimal cost of others when player J is in the market. Okay. Regardless, by taking away, so this is bid of player J, by taking away contribution of player J in the market, you're basically giving them incentive to be truthful because they cannot affect their own payment. The bid of player J is completely out of the payment calculation. Yeah.
This bid or only bid? Is it this bid of
all the bids of this player. The whole player is out of the game, so you don't give them incentive. Yeah, exactly. It looks kind of maybe confusing with the notation, but let's go through the example, then we will see what will happen. Okay. So let's back to the example. So this is called, by the way, the VCG payment rule. And the key is to take away player J's bid when you're computing the prices. Back to example. Okay. So P2 winner and P3 were also, they were winner. So what's the payment to P2? So what we'll do is we'll take away this player, and we see that, okay, if I want to get 800 kilowatt, what's the cheapest way I can do that? I need, well, I need for sure this bid, and then I need this one. So it's going to be 51, right? So it's going to be 25 plus 26. So payment to player 2 is going to be, so J star of x minus 2 is going to be 25 plus 26, 51. When player 2 was in the game, the J star of x was 48, and player 2's accepted bid was 30. So at the end of the calculation, this equation will give me 51 minus 48 minus 30. What do I get? 18. $33? Okay, good. Okay, so player 2 for providing her bid was 30 for 600 CHF, and she gets paid 33. And if you do the same thing for player 1, J star of x minus player 3, who is the other winner, if I take away player 3, then the cheapest way is 24 plus 25, so it's 49. So the payment is going to be 49 minus 48 minus their accepted bid was 18, 30, 40, 19. Okay. Is this clear? Yeah?
Can you imagine a situation in which once you delete one of the players from the game, then the game is not feasible anymore?
Yeah. Then that player has market power, basically. Yeah, exactly. So that's how it only works if you still get a feasible solution. Yeah. And that player could raise the prices, I guess, because this will not give you a feasible solution. The solution will be infinity or not feasible. Yeah, good question.
But VCG is supposed to not have market power, right?
But if you don't get a feasible solution,
Then there is no solution. But
so you have to suppose that if the system operator values getting this, procuring this at any price, then they will have power, I guess, because your value is infinity maybe for as an operator if you really want to get this, and there's no other alternative that provides. Yeah.
I think one example is transmission network. Right?
Okay, you're right.
If you eliminate transmission network to find its value, it's infinite. You don't know how to price it.
If you eliminate.
I mean, if you would like to pay transmission network,
Mm-hmm.
right? So how to
That's right.
find
Yeah.
the value of the transmission
Right.
network?
It's infinite.
It's infinite, right?
Because without transition network, you can't. Yeah, exactly. You need to have alternatives.
Yep.
Yeah.
Another question, sorry. So it seems to me as if the second price of that is just smarter than the first price option. But why don't we use that in electricity tenders?
Okay, we come back to that. That's exactly some of the things I've been looking on, Jalal. Also, there has some other problems with it. So the good side of it is incentive compatibility. So basically, by giving players more than what they bid, you're giving them incentives to be truthful. There are a few problems with second price, and I have another example which we can look at it briefly. Basically, the one problem you notice here is that the auctioneer actually ends up paying more money, but let's forget about that, because let's say that in the first price anyways they were overbidding, so it's not quite clear to say they are overpaying, because in this case they're bidding truthfully. But on a couple of more serious problems is that collusion. And you guys came up with a very good way. You had the second price and you colluded together and you shared the profit, right? That's exactly one of the problems of VCG. So by the way, there is a proof also why truthful bidding is the dominant strategy Nash Equilibrium in VCG, and you can go through it, and this is for the general setup. And then there's some other exercises. There's some other properties I briefly mentioned, and then I come back to your question of why we don't use it, right? And there's an issue Jalal mentioned yesterday, price recovery. You can show that by using the VCG, each player also experiences non-negative utility, so there's price recovery. So we're happy about that. At this Nash Equilibrium, truthful bidding. And then the other thing is that at this dominant strategy incentive compatible, I need to define dominant strategy for you in a sec. Yeah, Nash Equilibrium, then utilities of all players is maximized. So it maximizes, VCG also has this property that it maximizes social welfare. That's called social welfare maximization. I'll briefly comment about that. Just give me 1 second. So this, and VCG is known as the only mechanism that satisfies all this property. Okay, you had a question.
Yeah, it seems like a really nice setup, but it's also a combinatory optimization.
Yeah, that's another issue. we can discuss that as well. Yeah, that's about how to solve it, how to compute it. This is a mixed integer. I mean, in the example I gave you, it's a mixed integer linear program. It can be large. If we have to solve it day ahead is okay, but if you have to solve it in real time, it can be slow. But this is the amount if you're running VCG, you have to basically run this n times instead of 1 time, because you have to, or the number of winners times more often, because you have to compute not just J star of x, but J star of x minus J for every winner to compute the payment.
But you don't need to solve it sequentially. You can solve it in parallel.
You can solve it in parallel, exactly. So it's not, in our case, it's not an issue, but people who want to use this in sort of internet and fast auctions, they look at these computational issues. Yeah.
You mentioned that this system is more expensive because you pay a little bit more than a bid. But I mean, in the current electricity systems, often you pay the system marginal price, which is also more than some of the bids. So isn't this in the end then still cheaper?
It's another very good question. We come back to that as well. Is it at the end cheaper? I think, so there is it really depends. It's hard to analyze, let's say like this. But there's this beautiful result that I like to come back at the end of the lecture, which says that basically all mechanisms satisfying certain property, the expected revenue is equivalent under the Bayesian Nash Equilibrium. But we don't have yet the tools to kind of look at that, meaning that given that in first price auction people will overbid, they have only certain amount of power to overbid because they need to think about the second best price, right? So their overbidding amount is limited. And if we look at this, what is their Nash equilibrium in expected value, if you kind of associate some probability distributions to players types, and then you could look at revenue of VCG in Nash equilibrium, then you actually will get the exact same amount, okay? So that criticism that maybe we're paying more is not completely, as you mentioned, is not clear because they're overbidding in first price auction, and at a base Nash equilibrium, and in VCG they're truthfully bidding. We're giving them more payment, but they're not overbidding. So I hope that helps. We'll come back to that. But let me at least say the couple of other good properties a little bit more, and then we talk about the problems. Okay, what's a dominant strategy Nash equilibrium? So here you had the definition of Nash equilibrium. This is a Nash equilibrium. And then we call it a dominant strategy Nash equilibrium if this inequality also holds for all x negative j, okay? It means that regardless of what other players are doing, you're best off bidding truthfully. And this is a really strong result, okay? You don't have to worry about what you don't even need to think about there's a game. You just, as long as you bid truthfully, you're maximizing your profit in VCG, okay? So it's a strong property. And the proof of it is also in your notes. Why truthful bidding is a dominant strategy in Nash equilibrium. But okay, another property is that the price recovery. And then finally, I want to briefly talk about the social welfare maximization, because it's another thing we want from a mechanism. So the way to look at this is if we let J0 be the auctioneer's revenue, and the VCG outcome maximizes sum of everybody's revenue. So let's say at the dominant strategy, so the outcome at which strategy, at dominant strategy incentive compatible Nash equilibrium. And the reason is that if you just work out the amount that the auctioneer is making the payments and compute the utility of everybody, you will get that this is exactly equal to J star of T. Okay? So you can just show that, which was maximized by the auctioneer. Okay? So this is called social welfare maximization. So we want a mechanism to have this property ideally as well. Okay. But then let's talk about problems, because you all said, okay, why don't we use this in power market? And so one problem I've looked at with my student is the issue of collusion, actually. So let's just look at this example. So suppose that you want to procure 800 kilowatts, and there are 5 providers. Player 1 offers 800 kilowatt at 50 CHF, and the next 4 players, they just, each of them gives 200 for 0. They just say, we'll offer it for 0, okay? And of course, in pay as bid, you don't have any incentive to do this because you will just get 0 payment. But in VCG, what would happen is that these 4 players will be the winners. So you get 200 from each of them. And each of them, if you take away each of them from the game, then you have to buy 800. You cannot get a feasible solution with the next 3. So you have to buy the 800 at 50 CHF. So you will pay each of them 50 CHF. They become winners, even though they gave 0 marginal cost. And these 4 players could be 4 people who are colluding. So they're lowering their price, they're getting the extra benefit, and then they're dividing that together, okay? So one really obvious issue. Did you have a question? No. Okay, I thought I saw a hand. Are there any questions? Is the setup clear? So collusion is a big problem in VCG mechanism. So people have incentives to collude, whereas in pay as bid, they don't. And actually, we also showed that in LMP, you also don't have incentive to collude. But in VCG, you have incentive to collude. And from auctioneer's perspective, it's even worse because somebody was willing to give you 800 kilowatts at 50 CHF, but you ended up paying 200 CHF. Because you $200 because you removed to calculate VCG payments, you removed each of these players from the game, and you computed how much it would have cost to get 800, and you gave them that price. So the auctioneer ends up with quite a bad revenue because of as a consequence of this collusion. Okay, so this is one of the issues. The other issue is this notion of budget balance if you're doing a two-sided market. Basically, the idea is that because you're paying the sellers more to give them incentive to be truthful, and you're charging the buyers less because, again, you want to give them incentive to be truthful, you end up, as an auctioneer, you end up with a loss. Okay? So where do you bring that money to make sure that demand and supply matches? So LMP doesn't have this property. Well, of course, under the assumption, no, actually, it doesn't have this property without any assumption. Basically, you can show that you don't have loss. You can have some extra, you can make some extra money which you would give to transmission system operators, but you don't make losses. But in VCG, you can have, as an auctioneer, you can have loss. So yeah, these are some of the problems that, although it may seem like, okay, in theory it's very nice, but in practice there are some problems. And so there's a paper, so we looked at some of these problems in our work. Jalal, I know, looks at these problems also, especially budget balance, and there are some, but in terms of electricity markets, they're not as much explored, I would say, but a lot of auction theory people explore this, because in internet, adverts are auctions that are run every second, so there's a lot of auction theory that comes from computer science, and I think it's very interesting to bring those to our power market problems, those methods. And there's a paper that's called the lovely but lonely VCG mechanism, and it talks about all of these issues. But one of the things that I'm working on with my PhD student Orchard is under which conditions, for example, what sort of rules we need to put on the market to make sure that collusion is not profitable, or that you have some budget balance. For example, we won't have time to go into detail, but for example, if you ensure the price functions are convex and the constraints satisfy certain assumption, then you have that these J's are what's called supermodular, and you can make sure that collusion is not profitable. And the way the tools you use is coalitional game theory there. So you kind of look at if people can make coalitions to improve their payoff. They're really beautiful game theoretic questions that you can ask, or who should collude with whom. That's also the topic of coalitional game theory, or how can we avoid collusion. And by ensuring the cost functions and constraints satisfy some relatively stringent assumptions, you can make sure that collusion and shield bidding will not be profitable. So that's something that sort of is ongoing research. I think, but yeah, if you would like to read more, there are some references. And otherwise, I'll want to briefly, we have still maybe like around 20 minutes, maybe we go into games with incomplete information also. So let's, if you have questions until now. Yeah?
Yeah, I think here the auctioneer is somewhat in a constrained situation because he has to get the electricity, right?
Yeah.
He cannot say, well, if I don't like the prices, I don't buy. If you were going to add storage to this game, then you could have a reserve price. And then you could possibly reduce prices.
I see.
Or not?
Maybe, yeah. Let me think. But then I guess is a storage also somebody who's bidding in the market, or
maybe the auctioneer could have it. Maybe it's
okay.
Yeah.
Yeah, the auctioneer. Yeah, that you're right. There's somehow you need to. The auctioneer should not be so desperate, basically, to get this electricity at any price. And if you have a storage, maybe you can use your own. Yeah.
Then
you
it
have
would
to
be
still analyze, I guess. Then the auctioneer then maybe has some minimum, maximum cost she's willing to buy. Then you can include that. Yes.
Okay.
Then it kind of runs into this formulation of like a bilateral market, because maybe the outcome, you don't even have an outcome if both sides are not basically happy. If the auctioneer is not willing to pay any price, there is no transactions, basically. You can model that.
Mm-hmm. Yeah, exactly.
Yeah.
Okay.
Good. Other questions? Okay. Yeah.
So I'm just clarifying the obvious. There's a range of different option techniques, and these are just basically instituted by auctioneers to get the minimum price for the product, but also to do things like they might have other ambitions, like they might want to reduce collusion, but
yes,
or there's
correct.
a range of different constraints, but they're going in, they're setting up some kind of auction mechanism just because this kind of theory tells them that it's going to lead to a lowest price, or it's going to lead to some kind of optimal situation for them.
Yeah. So exactly. So there are two sides to the story. From the players, they want to figure out how they should play, what sort of a strategy. From the auctioneer is thinking, how should I set the mechanism that I make sure that there is the incentive compatibility property, there is social welfare maximization, my revenue, there is no budget loss in a two-sided case. What else I want? I want price recovery, non-negative utilities, which is also referred to as individually rational. It makes sense for players to participate in auction. So there are all these desired, you can have like a list of all the things you may want from the mechanism. That's what the auctioneer thinks. But there's some impossibility result that tell you cannot have it all, basically. So they have to decide, they have two choices. They can relax some properties. So for example, we can relax incentive compatibility, but ensure that we cannot have collusion. That's what pay as bid and LMP achieve, for example. Or you may say that we want to relax some other property and ensure some other property and define another mechanism. So it's sort of a question of what you want and how can you ensure it. There are also, in terms of collusion, something I've worked more on, there is a notion of if the outcome of the auction belongs to what's called a core, it's some concept from game theory, then you can make sure that collusion is not profitable. So there's some core selecting mechanisms that basically try to give you a payment so that the outcome of auction inside this core, which is just a large linear program constraints that you have to satisfy. So yeah, there are various properties you may want, and you have to figure out which ones are the most important and how you can satisfy that.
Cool.
Yeah.
Just curiosity. So, basically, this that we've been discussing is sort of from the point of view of the auctioneer, how to find the best strategy so that I get the minimum cost.
Yeah.
Is there a branch of game theory that studies the opposite? So given a game and being a participant in the game, how do I game the game and try to get the best out of that?
Sure. I mean, that's why we look at Nash Equilibrium, because that's what the participants will look for. Because it means that if I play Nash Equilibrium, I don't have any incentive to deviate unilaterally, at least. Yeah. So, for example, that brings us to the next topic. Actually, if you look at pay as bid, the players could ask, how should I bid to optimize my profit? And obviously, the bidders would say that the one with the lowest bid would say that as long as I am just a little lower than second lowest bid, I will win and I will make the maximum profit. Okay, and so you can show that in pay as bid, the winner should bid just above the second lowest price. That's the Nash Equilibrium strategy, and everybody else should bid their true cost, because anyways, if they bid anything lower, they will make losses. So then the game theory aspect of it is exactly answering that question. Does that help? Yeah. Okay. So you can think of more questions as I erase the board. Maybe they have one clean board. That's good. Okay. By the way, for example, Facebook and Google, they're running auctions for their adverts every second, and they have to compute the solution fast, and they're running some variants of second price auction. I don't know the details of it, but they have some publication about it. I don't know how true it is, the details of the mechanism. eBay is another auction. Online auction. But there are a lot of computer scientists that look at these problems because they can affect the revenue quite a lot by designing the auction. Another practically motivated auction is what's called frequency spectrum. So this was some big auctions both in UK and also in the US to different, I think, cell phone providers, how to kind of auction the spectrum, power spectrum among them. So they also ran some sophisticated auction for that to make sure these properties of the auction. And there's some, I think I cited some papers. They talk about some of failures of these auctions. There was one also in Australia, I think, that they looked at this and it had some failures, and then they changed the auction, and in UK as well. So it's quite an active area of research, not just in power system, and I think there's a lot that we can do in collaboration. Okay, so briefly, in the next 10 minutes, I'll introduce games with incomplete information. And so here the motivation is, we looked at, for example, in second price auction or VCG, we knew that the dominant strategy in Nash Equilibrium is bidding truthfully. So it means I don't know anything about other players. I know that my best strategy is to bid truthfully. But what about in other auction? Unfortunately, they don't have this property. So how do I decide how to bid? Okay. And so it's not hard to verify that in a first price auction, so if T1, Tn are the true values, which later on I will call types of player 1 to n, the Nash equilibrium is that winner bids just below the second lowest. No, wait. I'm always confusing forward and reverse auction. So let's say we are procuring electricity we get from the lowest bid. And so as long as I bid below the second lowest bid, winner bids just below the second lowest bid, everybody else bids truthfully. This is the Nash equilibrium. You can verify that. No one will have an incentive to deviate from this outcome, okay? But it brings the question of how do you know what's the second lowest bid, and how do you know like who's the winner, okay? So this is an instance of a game with incomplete information. So you don't know who else is participating, what is their true value, so you can't really compute your Nash equilibrium. And so that brings the topic of Nash equilibria in games with incomplete information. And to just, maybe I briefly tell you, the standard setup to look at this problem is through a Bayesian formulation. So you associate some probability distribution, a prior, on what other players' true value can be, okay? Bayesian games. So can I go 10 minutes later? Okay. Okay, is it okay? Since I started 10 minutes later, as long as it's okay. Good. Briefly talk about it. So this, just like before, we have n players. I'll try to wrap up quickly, but just give you the tools so that you can analyze this. And we have types, T1, type sets. T1, T2 for each player, and a prior distribution. Prior distribution on types. It's a probability distribution, D, on T1, Tn. Yeah, it's going to get a little tricky with the notation, given, but I defined it all here. Okay. So we have the action spaces, the types, a prior probability distribution on types, and the utility is just as before, but it's a map from types and actions to R. So for example, in the first price auction, your utility was the payment minus your true value. The payment depends on your strategy. That's why that's a map from K, and your true value is your type. That's why it depends on both of them. And then we can define, there's some examples that we don't go through it, but you can see here. There's the definition of Bayesian Nash. Okay. There we go. So we can define a Bayesian. So given that you have some prior on types, okay, you can compute your expected cost. Okay, your expected cost function. Okay, so let me just describe all of this. So if you know your own type, you can find the conditional probability D of T minus J, so condition J. So this is distribution of others type, conditioned that you know your own type. So this could be your true value. Yeah. Perfect. Thank you. So then you can compute probability so dj of t minus j conditioned on tj multiplied by your cost function, which depends on your type of others, and the strategy, which is a map from types to actions. Okay. So you choose a strategy, which is a map from your type to actions. Then you compute your expected utility. So this is expected utility of player J. Okay, and then we say that we have a Nash equilibrium. You see that here I was looking at maximization problem, so you just have to think of this the reverse. But it's the same idea. Instead of so you're choosing the best response strategy to everybody else's type. So for any other choice, your expected cost will be worse. Okay? So all it means is that you need to multiply your cost function with the probability that others have type T minus J, condition that you know your own type. This gives you your expected utility, and you pick a strategy that maximizes your expected utility. Okay. But I just give you one example of this because I think it's very interesting. So you can set this up. This is called the Bayesian Nash Equilibrium. It's quite a hard thing to compute in most games, but there is one game that's quite, it's relatively easy, and that's again first price auction. Okay. So remember, we said that we don't know the type of other players, which is their true value. But let's look at an example where we assume that their true values of other player is, so we're going to look at an example, first price auction with 2 players. And this is a sort of Alice and Bob are the 2 players. And we assume that their true values, so their types, is uniformly distributed and independent on some interval. So these two people are participating in the auction, and the auctioneer, and then they map their type to a strategy. Let's say X, Y, okay? And they don't know what the true value of the other player is, but they just give this prior. Let's say you can change the bound of this interval to anything, but let's say that they say that, okay, I don't know it, but it comes from it's from a uniform distribution. Based on this knowledge, I want to choose what I give to the auctioneer, and Bob thinks the same way. And using this, so then you ask, what's the Bayesian Nash equilibrium? So now we have some information, whereas in the previous case we knew the Nash equilibrium, but it required full information on the types and other players. But here we just say we don't know them, but there are some random variables, and you can compute Bayesian Nash equilibrium. And here I think I did this, yeah. Okay, it's the full analysis is in your notes, so you can go through it. But once you do all the calculation, you find that the Bayesian Nash equilibrium is xy equals a over 2, b over 2. So that means that Alice will bid her true cost divided by 2, and Bob will bid his true cost divided by 2. Okay, the calculation is in the notes. But why do I bring this up here? There's some interesting property of this, and you can generalize this to n players and first price auction. Okay, you just get, I think, a over n plus 1. X, the true values divided by n plus 1 or something like this. Yeah.
Is this result again for maximization problem?
Yeah, I looked at the maximization, so.
Because otherwise, I guess we would bid something higher than your true cost.
Yeah, that's right. I looked at the maximization. Yes. Okay. So you bid A over 2 and you bid B over 2. So this is a strategy because it's a map from your type to an action. But what you can then look at is what is the expected revenue, which brings to your question. So the expected revenue is, for the auctioneer, is expected value of this expected value of mags of A over 2, B over 2, given that these are two independent uniform distributed numbers. And if you calculate this, you get 1 over 3. Okay? Let me just double check. Was it 1 over 3 or 2? But again, the calculation is there in the notes. Okay. So for the auctioneer, because we know A and B are uniformly distributed in 0, 1, you find the maximum, Alice and Bob bid A over 2, B over 2. The maximum one wins. The expected revenue is 1 over 3. Now, in the VCG mechanism, truthful bidding is dominant strategy. So it's also dominant strategy regardless of what other types are. So X, Y is A, B. Right? Because we bid truthfully. We don't have incentive to bid anything else. And the expected revenue of the auctioneer, well, the auctioneer will then get the second highest price. So it's expected value of mean of AB. And if you calculate that, you get also 1/3. Okay? And so the point is that there's this beautiful result from auction theory. It's called revenue equivalence principle, okay, which says that, again, I think it was another Nobel Prize, which says that as long as the mechanisms satisfy certain property, in this case, for example, we had to assume independent prior distribution on the types, the auctioneer's expected revenue at the Nash equilibrium is the same. So it doesn't matter which auction you're running, your expected revenue is the same, okay? So that's very interesting. It's sort of, it makes me always think, do we really need to think so much about which mechanism we design? But of course, there are a lot of limitations because it assumes players have independent priors and they don't know other types. But if you think of a real auction these markets are repeated over time, whether power market or any other auctions. So players are gathering information, the incomplete information they know is continuously changing, and so this notion of Bayesian Nash equilibrium is not really, you're not playing at the Bayesian Nash equilibrium in reality. You're constantly changing your strategy, and it's much harder to analyze what's happening in this dynamic setting. But there are some theoretical results, and that's always good to keep in mind as we look at what is possible and what's impossible when you think about these problems. Okay, so I guess my time is up, and I just want to wrap up. Let me just go back to just say what we looked at. I hope you got a flavor of some of the game-theoretic problems that arise in electricity markets. So we looked at first games with continuous action, then auctions and mechanism design, and games with incomplete information. And I have more examples and references in the notes, so please feel free to go through it, and if you have any comments or questions, you can write to me. There are a lot of papers also cited. Just feel free to explore and see what you find relevant to go deeper into. So that's it, I guess. Like this, I just wrap up. Do you have questions, actually? Sorry, I should have asked that. Yeah.
You mentioned that so for this game with incomplete information, actually the players constantly get new information.
Yes.
So would it make sense to, instead of using expected revenue as a metric, to maybe try to use expected worst case and solve this distributionally robust?
Oh, interesting. So that's a good point. Maybe you can use the data online and try to do the worst case with respect to data you've seen.
Yeah,
it seems it could make sense, but it's very hard to analyze. I haven't thought about it, but it makes sense to use the data online.
Yeah, exactly. You could do some data driven.
Exactly. Yeah, it's a good point.
Okay.
Other questions? Wow, nice catch.
You mentioned that, like in Switzerland, you have there's some ancillary service market with some stochastic constraints or something. So can you tell a bit more about that?
Yes, I gave a reference also in the notes. I hope I did. If not, I double check. Basically, for the ancillary service market, it's a two-stage market. And one is week ahead and one is daily. So it's kind of like the markets you heard about yesterday. So you minimize cost of the week ahead and expected cost of the daily. These constraints come from, they have this requirement that probability of demand and supply mismatch should be less than 0.0002, something like that. And based on that, you get a constraint for how much you have to procure. That's sort of the idea. So they analyze a lot of past data and demand and supply and how much ancillary services they purchase, and they come up with these distribution functions of probability of violating demand and supply, and they want to make sure that this is below the probability of violation is below the accepted level. That's where the stochasticity comes. Yeah.
Okay. Yeah.
Because it's uncertain, because the demand is uncertain in the future. There's also uncertainty in supply, and of course you don't want in expectation this to be small. You want to have very, very high probability of satisfying demand. So, yeah.
Okay. Thank you.
You're welcome. Other questions? Okay. So thank you. I hope to see you or hear from you later, and with this I wrap up. I'd like to also thank the organizers for inviting me. It's a new experience for me. I had to think about how do I condense all these interesting topics in a few hours and make sure that it's relevant and interesting for you and fits your background. So I hope it was useful to you. Thank you.